Going then.
Yeah, I'll do a quick hello and then hand it off to you. All right, hello and welcome everyone to CFRG. If you were expecting something non-CFRG, you may want to go to another room. We're going to kick this off with some slides. As you know, Stanislav, who's online, is one of the chairs, as well as myself and Alexei, who are here in person. We've got a big long agenda today, so I'm going to hand it over to Alexei for the chair slides.
Okay, as a reminder, this session is being recorded. You all should be using either this local site tool or the full Miteco access. This is just a reminder that we are covered by IETF Note 12 and various procedural documents. If you've seen them before, great. If not, please have a look. Again, privacy is code of conduct. Yeah, just a reminder. So this is an IRTF research group. We don't make standards. We cannot make IETF do anything, but luckily they like to use the output of our work. Okay. Very quick agenda bashing from chairs. So we have an optional talk at the end if we have time. Chairs would like to swap Mike Onworth's and John Bradley's talk because we will have open mic discussion, which will probably talk about chem combiners. Any other agenda bashing? Okay, going once, going twice. Okay. I'll try not to read everything on these slides because this.
The speaker mic is turned off. Can folks hear us online? Please confirm on the chat that the speaker mic can be heard.
Yes, it is.
Yeah. Okay, great. Okay, so very quickly going through document status is we have a couple of RFCs published since. We have one in RFC editor's queue. I think waiting for one from our RTF chair. But other than that, there is nothing in ISG or RSG review at the moment. We have plenty of active documents. We have 4 documents which are either in research group last call. Some of them weren't officially closed, and there are follow-up discussions. And in one case, there is a Shepherd follow-up action. And various other documents got updated. If you find anything wrong on the slides, please tell chairs. We have one recently adopted document on RSA guidance. We also in an interesting position where we adopted a topic on hybrid PQ cams. So there will be a design team formed to compile requirements, but we don't have a document yet. And the rest are some documents. Some of them are expired and probably need to be revived. Any comments on this?
Oh, I got it.
Okay.
Sorry.
That's all right.
not Christopher Patton.
Chris Patton's in the queue. Can we approve him?
Yeah. How do you do that?
Oh, come on.
Okay, Christopher, you're first.
Yeah, I was just curious about if anyone in the room is an author of the cryptography specifications guidelines document, can you comment on where you plan to take this? I'm personally very interested in seeing this revived. Thank you.
Yeah, this is Nick, chair and co-author, and this has been delayed a little bit, but the next steps here are to open up this discussion around special characters and overall just add detail to the document and push a new one to the list for discussion.
Dan?
Yeah, thank you, Dan Harkins. So what happened to my DNH PKE draft that I was in the last call, and then I didn't hear anything about the results? And
I wasn't on top of this.
Oh.
That was
Needs Shepherd follow-up.
got it. Okay.
and I'm
Sorry.
being the shepherd,
Sorry.
so
Sorry.
that's all right. Well, making the slides was useful for chairs because we actually find out the things we haven't done either. So, okay. Okay, and just a very quick slides. We remind people periodically about that. There is a CFRG is kind of managing crypto review panel, which is used for reviewing documents for CFRG security area and sometimes independent stream. In fact, pretty much anybody can request reviews and ask for advice. So it was first formed in 2016, and now we are on the latest iteration. We have the new members listed, and well, Stephen Farrell was lurking, but he is now officially a member. So yeah, this panel is selected for a 2-year term. And with this, I think we can start presentations.
Hi, Colin Perkins. Just to echo my thanks to the crypto panel members. This is a really important activity. So thank you to the chairs for organizing it, and thank you to the members of the panel. It's very much appreciated.
Okay. John Matson first. Which one do we? Hold on.
Is your mic on?
Is this one?
Yeah, I think this one's dead. Should we? Yeah, it's okay. Grab this for now.
Excuse me, chairs, do you want me to signal for us to get another microphone?
Can you, yeah, now you can hear me. Good. Should I start? Yeah. So this is hedged. Okay, I think we should, do you want me to take this first? That was second. Yeah. So this will be about the working group document hedged ECDSA and hedged EDDSA signatures. Next slide. And a big discussion topic on the list was what name it should have. Now we have taken a decision and changed the name to hedged ECDSA and hedged EDDSA signatures. This aligns with most late academic literature, and also with NIST. Several changes. We have added a second zero padding block that separates the context from the hash of the private key. This was requested by several people and aligns with BSI. Incorrect or incorrect statement in EDDSA about the context fitting in a block. In EDDSA, we changed the order and added a 00 byte. Two reasons for this. We noticed that the old order collided with the old RFC 8032. I don't know if there's any vulnerability based on that, but it seems a good design to avoid collisions by design. And then Bernstein recommended to put the random SED before the context. In ECDSA, we clarified that SED was different in the two steps, but then in E raised that this breaks the design principle in deterministic ECDSA, that it aligns with HMAC DRBG. So we change it back. The reasons to have two random would be to improve security against second order DPA attacks, but we think this this protects about first order, and we think that's good enough. Then change some of the KMAC output length requirements and some editorial. And while in the last NIST has published RFC 186.5, so EDDSA and deterministic DSA, which this draft builds on, are now also NIST standards. And NIST has published the hedged MLDSA, which used the hedge mode by a draft version of it anyway, that used the hedge signing by default. And we also know now that NIST has not included a hedged mode. That was a request for 186.5. Next slide. And this is how the EDDSA construction looks now, the order and the padding. And then the green things are new. So now you have two different byte strings that should be padded to align with the block length, the cipher. And here is the construction for deterministic EDDSA. The only thing new in EDDSA is the second padding block, or a first padding block. And then some additional information. Next slide. Some open issues. Bernstein suggests allow switching the order of the random value and the prefix. Says that you should use if you are concerned about RNG failures, you should put prefix first, and if side channel are the top threat, then you should put SED first. I think Bernstein's reasoning makes sense, but I'm not sure we want to take the effort to have two different modes. I think the focus here is side channel attack. So my feeling would be to keep it as is, but open to see. Then second suggestion is deterministic interface. Bernstein writes that we should have a deterministic interface. I don't want to speculate what I assume he means an internal interface in the draft, not an external interface where the user inputs SED. And also writes about test vectors. I think a test vector set fixes this. Next. Then there was comment about a FIPS compliant mode where you put random as additional input to the RNG. was a suggestion from Cisco. There's a link to a Cisco blog that talks about this. I don't know if there anybody wanting this draft to write something more about this as a complement. Don't speak up. Then 7, algorithm naming. Simon suggests new names for the new modes. Today there was a discussion on the GitHub saying that they don't, I don't remember the name of the person, but they don't think that's a good idea as these are compatible with existing verifiers. So I think my current feeling is that we keep calling it hedged EDDSA or hedged ED with context, similar to randomized ECDSA and deterministic ECDSA, and this will be the hedged EDDSA. And then a comment from René, wants must instead of recommended. Also a comment on GitHub that recommended is probably the way to go. So, unless there's more comments, I will close that. Next step is to include test vectors. And as of yesterday, we actually has test vectors. Danny generated them already and published them on GitHub. So they will be included in the next version. These text vectors include message key and sed, and then you get the signature. And then there's been people requesting that we should have some proofs for the constructions. Of course, always welcome. I think you can discuss what kind of proofs these should be. I think the deterministic ECDS doesn't really come with any proofs, and I think my high-level feeling is that the proofs for EDDSA apply to this also. But that should be investigated and looked into. I think any people wanting to look at this is very welcome in all aspects. Yeah.
We don't have a mic, so
Okay, yeah. Any questions? Yeah, Christopher.
Can you go back to slide 5, issue number 3 on GitHub? So I'm somewhat concerned about adding this like kind of bit of flexibility in the recommendation. I'd like to have a clearer understanding of the motivation, in particular the second point here. Put whatever is least likely to be attacker predictable first. This makes intuitive sense. Do we know that this is actually an issue in this particular case? It seems like good general advice, but I'm wondering if it applies to the signature schemes for which this draft affects.
I don't. Now we decided to move the random value sed before the context anyway. But the main reason for this was that the old construction had some collisions with RFC 8032, which we thought it would be. It feels like the different modes in 8032 avoids collision. So we thought it would be a good idea to continue to avoid collisions, even if I don't have an attack. But yeah, the other suggestion, I think I get the feeling that we should not allow switching the order. We focus on side channel attacks.
That outcome makes sense to me.
Yeah, good. Yes. So this is new presentation, Galois encounter mode with secure short tags. Next slide. Was also presented at the NIST encryption workshop in October. So if you looked at that, this is very similar. So GCM has been used because it's attractive performance and provable security. During standardization, Ferguson identified 2 weaknesses. One is that this forgery probability increases with the message length, and second is that successful forgeries allows the attacker to calculate the authentication key. He suggested to go back to encrypting the tag. The authors argue that this would lower performance. As a comment to NIST, Nyberg et al. Suggested an alternative construction where you just do G-hash with 2 different keys, and they also show that has already done 20 years ago. This had already been proven to be secure in several papers. NIST did not follow this. Instead, they put some requirements, and now they're actually removing the whole Annex B. At least they are planning to do that. So short tags with GCM will disappear. There are other, CCM has very good security with short tags, but it's not very used. So people want GCM performance. Next, even if they have to eat. So there's many use cases of short tags. One is radio link layers, which often have 32-bit tags, including 4G and 5G. There, it's mostly hindering the attacker to change an IP address, and the encryption is mostly for headers. The information is encrypted with HTTPS anyway. Then there's another big use case is in media, especially for audio, where you have very small packages, and forgery of a single packet doesn't matter at all. It's barely noticeable because it encodes so little time of speech. And due to its weakness, CCM is typically not used, and then you have the alternatives is to use CCM or CTR with HMAC, which is slower. Next slide. So what is this draft? It's called then GCM SST, GCM with secure short tags. It follows the recommendations from Nyberg. It's just an implementation of that. Nyberg does not specify everything, so there's some options for how to derive the keys, for example. We just do this as a key stream. GCM SST like GCM is defined as a general construction, so you can use any key stream generator, not just block cipher. 3 differences. There's an additional sub key. GCM has 1 authentication key H. This adds another. The keys are freshly generated with each nonce. And then we use polyval instead of G-hash. And polyval is the little endian version of G-hash, which is more efficient in basically all modern CPUs. And G-hash and polyval can actually be implemented in terms of each other. And this mode, GCM SST, has been chosen by SSH and 3GPP for use in 5G and very likely 6G. That decision is already taken, and this is it's not the same specification, but they are technically compatible with each other. And there's been strong interest in IETF for media encryption applications. And I also have a presentation on this in AVT Core tomorrow. Next slide. So how does it look like? Everything is green, is the new things. So the difference is polyval, as I said, a new key Q, and then there is always 2 key generations, J1 here and J. H, both H and Q are derived fresh every instance. And that's the differences. And performance-wise, there's 2 extra AS invocations in the beginning, but that is compensated by the faster polyval. So in speed testing, they are basically identical, was what my performance tester said. Next slide. Decryption is basically, same changes. This is if you know GCM, this is GCM with these changes. Next slide. So what are the properties you get? So performance very similar. Tag sizes, this can then support short tag sizes. And for short tag lengths, in GCM, the security of short tags is the tag length minus the logarithm of all the blocks, number of blocks in the plain text and the AAD plus 1. In GCM SAT, it's proven that you get instead you get T-bit security as long as your plain text and AAD is not longer than your tag is shorter than 128 minus the same logarithm. We have adapted the GCM allows very big AAD. We have decreased these, and also the plain text is decreased because we have 3 keys instead of 2. The AAD is decreased so that we get the smaller logarithm input. And with that, with these requirements, you can get 96-bit, up to 96-bit, 5-bit tags, you get almost perfect security. If you decrease the plain text and so on, you can ramp this up. This is mostly useful for short tags. For long tags, the security if you have 128-bit tags, the security properties are very similar to GCM. And it does not solve nonce reuse. You get some more terms in the equation. So you get like for full tags you need 3 nonce collisions instead of 2. And as Scott wrote on the mailing list, if you have short tags, of course you need more, like 9 in the example he gave. Next slide. So this is a quite small modification. Old known construction with proven security. It does not only work for AES 128, it works for any cipher that can generate key stream. So Randall 256-bit blocks or a stream cipher. Performance-wise, it's very similar to GCM, and we think it's not only useful in 5G, but also for media encryption, especially audio in, for example, SRTP and S-frame. So would CFRG be interested in working on this? I think the draft is in a very, SSH has worked with this for several years. I think the draft is in a quite good condition already.
I have a microphone now.
Yeah.
So any questions from the audience, comments on this? If not, we'll discuss as the chairs. There's sort of a lot of work going on in different directions around block ciphers and block cipher modes. So yes, okay, we have Chris in the queue. Chris?
I could ask less questions if that would be preferable. I have 2 questions on this one though. The first question is, are there working groups at IETF who need this, or we think they might need this? The second question is, how much room is there to change things if like CFRG decides it wants to, I don't know, tweak it so that we can have a 128-bit nonce instead of a 96-bit nonce? I'm not saying that's a good idea. I'm just saying like what sort of changes are on the table, if any?
Yeah, I think this is in a good shape. If CFRG wants to change something, then CFRG changes something. There is no need to be compatible with what is used in 5G. It's just that that's a good basis to stand on. I'm going to present this in AVT Core tomorrow, so then we know a little bit more about SRTP interest. There was interest on the mailing list in SRTP and S-frame, and also some quick mailing list, media over quick, I think, in the past, but nothing formal. But we'll figure that out. I cannot.
Yeah, it'd just be good to know, like, specifically what purpose this will serve.
Yeah, I think media encryption, mainly audio, I would say. Yeah.
Anybody else in the queue? Let's see, we've got Chris. Deirdre's up next. So, all right, thanks, John. Thank you. Let Deirdre present remotely.
Let's see if it lets me control these slides.
I'm sorry. Hello. Can I? My tooling was down. Can I make a quick comment about audio? In my experience, audio doesn't need that high performance, and so the traditional solutions of using HMAC works quite well.
That was Scott Fleur for the record.
We good?
Go ahead, Deirdre. It's all you.
Cool. Great. I'm going to go pretty fast, so I'll just jump right into it. This is a proposal for a way to use MLChem as a pure post-quantum cipher suite for HPKE public key encryption. This is someone came to me and asked, what would I use? A tool set, a software implementation, a specific construction for how to do public key encryption in a post-quantum way. And I didn't have a ready answer for them. So I basically went looking for ones based on HPKE because it is modern and good and nice. And I didn't really find one. So you may know the X-Wing draft that we have proposed a couple of weeks ago, which is a hybrid chem. And we could look at that one. But we know that MLChem is about to be finalized as a FIPS standard, as FIPS 203, knock wood. It should be landing in the summer, maybe. So I wanted to just write that down. It was like, if we want to do something clean and straightforward and just slot MLChem in where the Diffie-Hellman stuff in HPKE is, it should be really easy, right? So I wanted to just write that down, pair it with HKDF SHA-2 and AES GCM, and just write it down and just say, here is a thing one could use and feel pretty good about it if you completely trust MLChem for your post-quantum asymmetric cryptography. And this is pure base mode for HPKE. We're not doing anything with auth mode. I didn't even look at pre-shared key. Pre-shared key may work fine, mostly because we don't really know how to do auth mode with some of these post-quantum chems. So I just didn't look at it. So here are the requirements of the HPK RFC. Basically, it has to be the chem that you're slotting in to your cipher suite has to be shaped like a chem with a keygen, an end caps, and a decaps signature. And that chem has to be in CCA to secure indistinguishability under chosen ciphertext attack, or adaptive chosen ciphertext attack. You'll see later that in the chem setting, this has been kind of lifted over from public key encryption. They just say in CCA, full stop, and that it just means the same thing. So if you get confused about that, I got confused about that too. It means the same thing. So these are our requirements according to HPKE. So we look at the draft for MLChem. It says that it has these security properties. Elsewhere in the document, it has the signature for the scheme. It seems like we're good to go, right? Do we have to do anything else? Well, there's been recent work in the past 6-ish months, maybe, about re-encapsulation attacks when integrating chems in higher level protocols. And the paper that has formalized a lot of the security properties that are written down in kind of more of a symbolic model, what these re-encapsulation attacks kind of look like in different settings, has been done by Cass Kramers and his group. I'm going to be talking about this paper a lot. And the first work to really make it salient to me that we have to be careful and we have to look under the hood of some of the chems that we're integrating in higher level protocols, is using some of the research from Kramers et al. In analysis of Signal's new PQ XDH hybrid post-quantum secure session setup that they did migrate to with the help from analysis from the Crispin team. The first version of their PQ key establishment relied only on having an in-CCA chem in it. And they basically found that depending on the implementation, the specific FO transform of the chem, that would be vulnerable to re-encapsulation attacks. Luckily, signal specifically made a change, but they were also specifically using Kyber, not MLChem, but Kyber. And so they were secure from this attack, and I'll get into that later. So this is a little bit more detail about that, and there are links in these slides for you to run that down. So I wanted to look specifically at how DHChem, which is the current default of all the cipher suites in the HPK spec, actually was constructed, and basically do like a dirty analysis of its properties to see if MLChem would be fine and match up. And so this is looking at what's actually in the spec, and then the key schedule in HPKE, which consumes the output of DHChem. So it's looking at what the actual chem is doing, and then once you've spat out a shared secret at the end, what is the rest of HPK doing with that or any other information. So in here, we can see that when you do an NCAPS, you take your ephemeral public key, which is basically your ciphertext for any other chem. You take your long-term public key, PKR, you serialize them and you concatenate them together, and you shove them through your extract and expand, which is basically your KDF inside this, this chem definition. And what this does is it gives us the strongest binding properties that you can get under the formalizations from Kramer's et al. And we don't have to worry about an attacker who can manipulate anything on the wire. If they manipulate the ciphertext, it'll have a different shared secret. If it manipulates the public key, it'll have a different shared secret. So the shared secret binds the ciphertext and the public key, and bind has a specific, definition in the paper, against a malicious adversary. A malicious adversary that can manipulate key material and basically try and do whatever it wants. The key will change. So this is related to other earlier properties like contributory behaviors or something like that. Other times people have called this sort of thing robustness. So that's what DHChem gets you. And then if you look further down to HPKE, basically HPKE relies on the shared secret and nothing else about the chem, nothing about the public key, nothing about the ephemeral public key in DHChem's case, or the ciphertext in any other chem's case. They just take the shared secret out the back of the chem, and it just proceeds and doesn't bind anything else into the key schedule. This is different than, say, your TLS 1.3, where it's just, hashing everything in the transcript, like the message transcript of the protocol into the KDF. So I just wanted to kind of point that out here. So this is kind of lining out what I just said, which is that the binding properties of DHChem mean it is safe to take the shared secret out the back of DHChem and just not have to do anything else like hashing in the public key or hashing in the ciphertext, which is in this case the ephemeral public key, into your key schedule, because the shared secret already tightly binds the public key and the ciphertext. It will change if those two things change. So that's great. That means DHChem is great, and it's a very good chem, and we really, really like it. But MLChem is not the same. Spoiler, Kyber is the same in terms of these binding properties, but MLChem is not Kyber. So looking at Kyber, what we're doing when we're doing a decaps here, this is from the draft for FIPS 203, we take the hash of the public key, the encapsulation key, which is part of the decapsulation key, and we commit to that. We hash that in with the decrypted message here. And then if we correctly re-encrypt the message and do all this stuff using the key material and confirm that we actually, everything passes, then we have tightly bound to the public key. But whether we bind to the ciphertext C up here is completely dependent on the, I don't know if you can see my mouse. It's completely dependent on the properties of KPKE decrypt and encrypt, which is like another layer of non-obviousness. And I'll skip to the end and basically say that also in the X-Wing paper, but other areas, that MLChem is chosen ciphertext resistant, which is equivalent to a slightly weaker binding property than the kind that the DHChem has. It's leak bind. The shared secret binds in a leak resistant manner to the ciphertext, not in the malicious against a malicious adversary. Leak basically says if all the key material is leaked, but it's not manipulated with, are you resistant from an attack? And it is, but it's not as strong as, say, a malicious adversary that's doing whatever they want to it. And this is due to the properties of the public key encryption algorithm underneath. And I'll show some more citations for that later. This is not catastrophic, but it's not exactly the same as what we've been relying on with DHChem. And I will make an argument that in MLChem's case, this is not the end of the world, but it does matter for other chems because all the HPKE standard says is it needs to be an in CCA chem, right? It doesn't say anything else about any of these other binding properties. So for example, one other post-quantum chem that's been in the competition, the NIST competition, and kind of floating around is based on other security properties is classic Michaelis. This is from the NIST submission standard for classic Michaelis. It is an in-CCA chem. Oops. Okay, I don't want to do that. So that fulfills HPKE's requirements. It does tightly bind the ciphertext down in here. So on line 4, we hash in the ciphertext, which is passed in. So the shared secret, and the shared secret is the result of that hash. We don't manipulate it anymore. So when the ciphertext changes, the shared secret will change. But kind of similar to MLChem, the binding properties of it binding to the public key are completely reliant on the public key encryption algorithm properties. The robustness, which is kind of, explored by Grubbs et al. In kind of one of these citations here. And what they found in their analysis of HPKEs that for MLChem, there's so many acronyms, I'm sorry. For classic Michaelis, for any plain text M, it's possible to construct a single ciphertext C that always decrypts to M under any private key. So that means I can encrypt to, Chris Patton's public key, but it will decrypt under, Nick Sullivan's private key. And that's just a feature of classic Michaelis, and it doesn't violate the in-CCA security game. So what this means is that there is no binding at all to the public key in classic Michaelis as a chem. There's no leak, there's no mal, there's no even honest. There's if everyone behaves, there's no binding at all. And basically this is you slot this into HPKE, it obeys all of the, requirements of HPKE, and it'll blow up in your face because it'll just let you decrypt to somebody, encrypt to somebody else, but it'll decrypt to me or something like that, or anybody else, because those are the properties of the chem, and HPKE relies solely on the properties of the chem for this sort of stuff. And I'm going to keep going because I'm running out of time. So basically what I'm saying is that the way it's currently written, the chem properties really matter. So if we want to use MLChem and match, basically saying DHChem is really great, we just want to match it. Let's try to match it with MLChem instead of using it raw. And you just do another extract and expand. You put in the ciphertext along with the shared secret you already got out the back end, and you're done. This doesn't pull in any other requirements from any other part or any other things. It's really straightforward. You get your malicious binding to the ciphertext, and you already have your malicious binding to the public key. You match DHChem, you're done. But this is kind of hand rolling it for MLChem specifically. An alternative is basically changing HPKE to do what ideally it would have done in the first place, which is to always have it bind to the public key and the ciphertext, no matter what chem you're slotting in there. The downside is this is already a fixed standard. It's already been deployed. It's already been implemented in a lot of places. The pros of doing it this way is that you would avoid having to look at any other chem and its binding properties about whether it's safe to use it in HPKE. It would just really bulletproof you and belt and suspenders you and get you nicely in line to what your expectations were for DHChem. And you can enforce it for any of these. And it would basically allow you to do classic Michaelis safely if you wrapped it like this, if you did them all wrapped like this. And I will go back, and basically I talked to one of the HPK co-authors, and basically they said they agreed, and they thought this is kind of one of the design principles that HPK should have, and it does have just for DH Chem. But it's written in there that they want to allow other cipher suites and other chems in there as well. So yeah, so I have a draft that's specific for ML Chem, but we have an alternative of how we might want to approach this, and I welcome questions.
Okay, thank you. This type of analysis is super valuable, even if it's post-publication of the RFC. So we have Chris in the queue.
Chris Kwiatkowski. This is cool work. I really like it. Somewhere in the draft you say that you mentioned that the MLChem is implicitly rejecting. And do you need also those binding properties for when there is a decryption failure?
No, it includes. Are you talking a decryption failure on the HPKAE level or in the chem
on the
level?
MLChem level.
All of these binding properties include modeling explicit and implicit rejection. There's like a subset of the full assortment of binding properties that can exist that basically fall out if you are implicit rejection. But all of the chems that are, except DH chem, I guess. Well, no, not really. These are modeled explicitly in looking at whether it's implicit rejection or explicit rejection. So if decryption fails in that step, it returns the rejection value or something like that. And that is included in these notions, these formalized notions. I hope that helps.
Cool. Yeah. Okay. Thanks.
Hi, Rowan May, currently unaffiliated. Thank you very much for this analysis. I had one comment on the use of MLChem without hybrids in general, which is I can think of two specific places where I think this is useful. One would be in TLS, where you don't need the guarantees of HPKE, which would be like an MLChem VPN, like a MLChem TLS VPN to cover traffic that's otherwise already encrypted with classical crypto. And the other would be if I've got classical crypto and then I want to do JOTs of various kinds, auth tokens and things like that, and I could use HPKE with MLChem inside there to encrypt those tokens so that I get both, both classical and post-quantum resistant.
Neat.
But this kind of comes back to the what are the priorities of CFRG, and particularly what are the priorities with respect to things that people in the IETF need, and for MLS, I'm really would love for us to get X-Wing done, so we have some concrete, easy to use chem that we can reference in a cipher suite. It's really tempting for people to come and say, let's go and do a generic solution. But unless you can come up with at least an existence proof for generic solutions, let's go and do the concrete, obvious thing first. And that doesn't prevent you from going and doing a, RFC 9180 BIS to patch HPKE later. Thanks.
So as a reminder, HPKE code point registration is only a document required. It's not an expert's review. So whether or not this particular draft would be exactly compatible with 9180, I'm not sure. Maybe Deirdre, you would know exactly what the differences would be, but it may be possible to get a code point with this draft without it being adopted.
Cool. I think because it's defining its own cipher suite and it's explicitly defining like just a little bit of extra, like I could just write down MLChem with a tweak like in full and be like, here's my new cipher suite, but it's like, it's just a shim layer basically around MLChem. I think that would be fine as its own cipher suite. And then later, like doing, you know, a patch version of HPKE that would make it moot could also be a thing that happens. They're not blocked by the other or something. So
Yeah, there's a number of different directions we can go in, but 9180 bis, as suggested by this presentation, is not out of the question.
yeah. Thank you.
Thanks. Chris Patton, you're up.
All right. Can I control the slides? Okay. All right, sweet. Okay, changing gears here. So this is an update on a new draft that was presented at 118, a protocol called Mastic. This is kind of fitting into the VDAF framework and the stuff that we're working on for the PPM working group. I'm going to give a quick update, and then I want to have like a broader discussion about how CFRG should govern the development of these protocols that are kind of new, I think, to a lot of people in the room. So if you fall asleep during this, please wake up for the last few minutes. Okay, so the problem that we're solving with this protocol is called the heavy hitters problem. So this is something that PPM would like to have a solution for. What we want to do is we have a bunch of clients and they're uploading bit strings, and then we want to count, we want to find out the bit strings that occur at least T times for some threshold T. So just as a running example, imagine that we want to know the most popular websites visited by the users of our web browser. So it comes up in a lot of different ways, but that's kind of the canonical use case that people think of. So we already have a solution for this in draft IRTF CFRG VDAF, this protocol called Poplar 1. So what we're doing in this is basically multi-party computation, secret sharing multi-party computation. In this protocol, we have two aggregation servers that we need to trust to be non-colluding. We need to trust that one of them is honest. They are computing a secret shares of this thing that we call the prefix tree. The prefix tree for a set of strings is basically build a binary tree where each path is a distinct possible input, and then each node is the number of inputs that are prefixed by the path to that node. So for example, if our bit strings are 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 0, 1, we can see by inspection that 3 of these strings begin with 0. So that's why the left child of the root has the label 3 on it. So yeah, we're going to traverse a subset of this tree while we're doing this computation, and we're going to reveal the prefix counts along the way, so the values of the nodes. And so that's the basic idea of how Poplar works. It's a very efficient solution to this problem. We need an additional property besides. So what this guarantees is that we only learn, the aggregators only, well, the attacker only learns the subtree that we have traversed along the way to computing the heavy hitters. Another property we need is called robustness, where we want to make sure that no client can like poison the input by, for example, voting twice for 2 possible inputs. And we have this 2-round little multi-party computation that the aggregators run with randomness provided by the potentially malicious client. So Poplar is nice. It's kind of like a proof of concept that shows you can really do this computation quite efficiently. However, we've been working on an alternative. The reason basically is what we're finding with VDAFs in practice is we need to get as much functionality out of each protocol that we can. So for this new VDAF, we call Mastic. So we want to support first and foremost this use case called heavy hitters, but we also want to support a more general variant that we call weighted heavy hitters. And the goal here is very much the same. We have each user submitting a string, but it's also submitting an associated weight. And what we want to do is find the strings with the highest total weight. So for example, extending the URL example, imagine we want to know what are the highest engagement websites. So which users are like what are the websites where users are spending the highest average time on, I don't know, on TikTok or whatever the website is. And then there's this other use case that's actually specifically came up when talking about how Prio3 works. Prio3 is the other VDAF that we have in this document. What we can do with Mastic, we can get Prio3 style metrics, which is basically like any aggregation, simple aggregate that you would want to compute, you can compute with Prio. And we want to be able to group the metrics by specific client properties. So if you're a web browser vendor, you might want to know, you might be tracking some health metrics across versions of the browser. So you have like, imagine you have a dashboard where you're seeing like the load times for a specific page across all versions of your browser. So Mastic not only solves more use cases, it's also more efficient and has a much simpler and I think nicer design than Poplar. This has kind of two core components to it. First, we generalize this primitive that's used in Poplar called an IDPF. We generalize it into a VIDPF. And this is based on a paper that's a couple years old now from Eurocrypt. This is it's pretty lightweight. It's based just on hashing, and it sort of like implicitly provides a property that we need from it. And we also replaced the two-round MPC thing I described before with just evaluation of a fully linear proof. Well, that is a distributed evaluation of a fully linear proof. This is the core component of Prio3. This is a primitive we understand very well, and we have a nice implementation of. And it also just requires one round, so the overall Mastic is more round efficient, and also, and I'll skip that point altogether, given time constraints. So so what we've done since it was presented in Prague last year, we've begun security analysis. There's a paper you can read here. That paper is in submission. It has proofs of privacy and robustness, basically for the composition of its primitives. We still need a little bit of work to do to get concrete bounds for the primitives themselves. A lot of this is already kind of implicit in prior work, but we do need to put it all together for Mastic. And then we also are working on an implementation in Rust in the libprio library, for folks who are familiar with the code that's we're developing in the space. So the goal for the next draft is we're working on aligning the reference implementation with the security analysis and also kind of improvements that we've come up with while working on the actual Rust code. So kind of just feeding this feedback loop. So we think this will be ready for an adoption call at the next IETF, not this time. So what do we want? I basically want two things from you all today. I have kind of two questions. So this first one is really just helps us kind of pick a lane. We've already talked a little bit about this on list and off list with various people. Question is, should we replace Poplar 1 with Mastic in the base VDAF draft? The idea being that if Mastic is clearly better, then we should just replace Poplar with it so that there's not two solutions floating around for the same problem. The consensus so far is seems to be to adopt the Mastic draft and then only consider removing Poplar 1 once we are more comfortable with Mastic and are more certain about that it's always going to be better. So I'm happy to pick this direction, but I wanted to give anyone who has strong feelings about this an opportunity to push back. So chairs, if you want to open it up for questions real quick.
The queue is open. Questions or comments about the direction for Mastic? Okay, nothing in person. We can take this to the list. I think it's an important question.
All
Okay,
righty.
we have Tim.
I mean, I think, yeah, that sounds fine. I think we've already settled it on list. But okay, yeah, that's fine. Okay.
We have Tim in the queue. Tim has just entered
Oh,
the
go
queue.
ahead, Tim.
Thank you. I don't have anything too substantial to say. Just wanted to express my support for Mastic. In particular, as I think Chris might have explained, sorry, I was distracted answering questions in the chat. Besides the features that Mastic has that Poplar doesn't, it is also way, way, way faster. Poplar requires 2 rounds of communication between aggregators to prepare a report into an output. Mastic just 1. So even if it had no features beyond Poplar, it would be an enormous performance win.
Okay, thank you.
Okay.
Chris?
Is there anybody else in the queue?
No.
Okay. This is the last question I want to ask. So yeah, I mean, so I've been thinking about this problem of with talking about this with various people. I want to ask what people's thoughts are on how we should govern all of this work. So there's a lot of like protocols that fit into this VDAF framework. 2 of which we've adopted. Mastic, which is might be adopted, and this other one called Pine, which you'll learn about in the next talk. And we expect that there will be others. Well, at least we hope there will be others. Not all of these necessarily need to be endorsed by CFRG to get deployed, but nonetheless, we hope the feedback will be useful. It's also important to note that VDAF is kind of a subset of this thing we call multi-party computation, and there may come a need very soon, in fact, to develop other MPC techniques that don't fit neatly into this framework. So I think there will be a question here for CFRG to answer, which is like, what are we going to do with all of these different protocols? Is it up to CFRG to develop specifications for, or rather develop documents for each of these?
Okay, I don't think you're going to get any more comments from the room today on this, but thank you for the presentation.
Okay, well then I'll just end with a plug for Martin Thompson's side meeting tomorrow to discuss a related topic. It's called Other MPC for Measurement or something like that.
All right, thank you. We have Junia Chen.
Thursday, 2 p.m. Not tomorrow. 6 and 7, P6 and 7, I believe.
Hi, chairs. I just requested to control the slides, if that's possible. Cool. All right. Can everyone hear me okay?
Yes.
Okay. Hey, everyone. So continue from the VDAF talk from Chris. I'm going to give a quick update of new VDAF called Private Inexpensive Norm Enforcement, which is a new VDAF to support federated machine learning use cases, a new use case for the PPM working group. And this is a joint work with Chris Patton. I'm going to briefly talk about the use case first. Here I have a list of devices on the left. Each of them trains a machine learning model denoted as F here with its local data. Each client then generates a model update vector, which we also called gradient. And to improve the machine learning model, we have this central server on the right that collects the gradients from the clients. The server then aggregates the gradients and applies the aggregation to the model. And then we get an improved model called F prime. And we'll send this new model back to the clients to repeat this process in the next iteration. It is great this process doesn't require us to collect the client data directly, but the model gradients still leak very sensitive information about the clients. So we want to see if we can better protect client privacy here. One solution is to leverage the VDAF framework to remove this trust on the central server. So VDAF is a secure multi-party computation protocol that can aggregate client measurements with privacy and robustness. And the base VDAF draft specifically provides a spec for Proof 3, which uses the idea of a fully linear proof, which is basically a distributed zero-knowledge proof system to verify certain properties of the client measurements. And this ensures we don't learn anything about each individual client measurement, but still able to ensure the robustness of the system. Therefore, we have proposed this new VDAF called Pine, which is based on a recent paper with Guy Rothblum, Eran Omri, and Kunal Tower. This new VDAF is to compute an aggregation of the client gradients expressed as vectors of real numbers. And to ensure the robustness of the aggregation, we require each client to have a bounded L2 norm, which is defined as taking the square root of the sum of squares of all gradient entries. It uses the similar idea of a fully linear proof like Proof 3. And let's see how it works in the diagram. Here I basically replaced the central server with two aggregators, one leader and one helper. And the collector will collect the aggregations from both aggregators. What client does is it encodes its gradient into a vector of field elements and generates a proof to prove its L2 norm is bounded. And then secret shares its gradient into a vector, and secret shares into secret shares for the two aggregators. The aggregators then compute the results over its secret or their respective secret shares and sends their shares to the collector. And then the collector will combine the two aggregate shares and produce the aggregated gradients. And as before, it applies the aggregation to the model to obtain a new improved model F prime and send it back to the clients again. So why do we need a new VDAF to support this? Why can't we leverage Proof 3 directly? Because computing the squared L2 norm in the field element operations can overflow the field modulus. So for example, if my L2 norm bound here is 10, and the field modulus Q is 23, and I have this clearly invalid client gradient that is 99, 0, and 7, taking the squared L2 norm modulo the field size is only 6, which can cause the aggregators to incorrectly accept this client gradient. And as a result, we will corrupt our machine learning model, and we certainly do not want that. So the central challenge here is to prevent or detect this wraparound effect. One solution with Proof 3 is we can ensure each entry of the gradient is sufficiently small. For example, by representing each entry of the gradient as bits, but the communication cost of such approach would be extremely high, so which is infeasible for some large dimension. So Pine provides this innovative idea of checking for this wraparound effect. The high-level idea works as the follows. A random vector will be sampled, and each entry of it is -1, 1, or 0. And we'll compute a dot product of the random vector with the encoded gradient. And if the squared L2 norm of the gradient wraps around the field modulus, this dot product is likely to be large. And our paper proves this check can correctly detect wraparound with probability a half. And in order to achieve the desired soundness error, we basically repeat this check many times. And we want to know this is incompatible with Pro 3 because we want the clients and aggregators to independently derive this random vector on their own. And finally, some performance comparisons. Suppose our auto-norm bound is 1, and the number of fractional bits to keep in each entry of our gradient is 15. And on dimension 100K, Pine's communication cost is 15 times less compared to a solution with Pro 3. And finally, some next steps for this draft. Currently, we have finished the core design work and have provided some reference code and test vectors. And as a next step, we want to complete the draft text and finalize the parameters to minimize the communication cost. And in the meantime, incorporate feedback from the implementers. And our questions for the research group is CFRG interested in adopting this work because this can enable a new use case for the PPM working group. And we certainly welcome more security analysis from the research group. Thank you.
All right, thanks. Any questions? Oh,
sorry, I can't get my
Roman. Yep.
My Wi-Fi keeps dropping. Hi, Roman Jinliu. So the question about support for PPM, has the working group decided that they want to work on this particular use case? I'm kind of wondering, chicken egg. Does the group here need to work on it to support that use case? Is the use case already agreed upon and we need CFRG support? Can you give us a sense for that?
I think this is a new use case, and we basically just proposed this in the mailing list for PPM, and we're asking for feedback there as well. But we just want to sort of start the draft that can enable this use case. But we're also asking for feedback from the PPM working group as well.
Thank you.
Chris, you have any comments?
Right. Yeah. To be very clear, we haven't got the PPM group has not asked us to adopt this work.
Yeah, it's not in the charter right now. This is a new use case for PPM that it still needs to discuss. Absolutely, it's something that Junier and I have had lots of conversations in and outside of PPM. But yeah, it's not formally part of the charter.
Martin.
Yeah. So Chris already plugged the talk away, the side meeting that we're having later on this week. This has some interesting implications for the balance between the work that a client does and the work that is done by the servers. And there's a couple of points in this space that we've been exploring ourselves for this. And so it would be good to have a discussion about that, I think, before sort of firmly concluding this. But I think that discussion needs to happen in PPM rather than here. And once PPM has decided on the use case and has some thoughts about maybe how it wants to approach the problem, then we can have a better discussion here.
Sounds good. Thanks for the feedback.
Thanks for the presentation. Our next talk, as mentioned, we switched the last two speakers. So Mike, you're not up. It's John Bradley. Yeah. Oh. There's not much room here, though. Yeah.
Okay, oops. Am I supposed to stand on the X?
Please. These cameras can adjust, so you don't have to.
Okay. So I wanted to introduce this draft to get people thinking about it and provide some feedback. You can. So the first thing I'll admit is that asynchronous remote key generation may not be the best name for this in the long term, but that's the name that I inherited based on the research. We can go to the next slide. Okay.
We don't have a clicker for you.
So we submitted an update. The origin of this comes from WebAuthn/FIDO, where we were originally looking for a way of doing credential recovery. That work kind of went by the wayside when Apple and Google and others decided that sharing public keys amongst devices was a good thing, which meant that relying parties were unlikely to do a bunch of extra work to enable recovery of credentials because they just copy it between devices. So our original work on being able to have a cryptographic method of being able to recover credentials without sharing the private keys across devices came to nothing. Then we got involved in the European large-scale pilots for credentials, national IDs, etc. And it turns out that, you know, when you invent something for one thing, sometimes you discover it's really useful for something completely different that you never originally anticipated. So we're using the same techniques. One of the problems with verifiable credentials is that you need a proof key for each instance. So using this technique, it enables you to generate a public key and a blinding factor, which can then be used to generate, then be given to a wallet, which can then generate any number of public keys for creating instances of verifiable credentials. And a secure element can then take the key handle and the public key and generate the appropriate signature for the verifiable presentation if you follow the flow of verifiable credentials. So this technique enables wallets to essentially manufacture any number of public keys that are non-correlatable. So the properties of this are that the public keys that are generated off of the public key seed are non-correlatable, and there is no way for the holder of the public key seed and the blinding factor to figure out calculate the associated private keys. We have some feedback and a number of formulations for making this post-quantum resistant for those that are interested in that. The draft has all of the appropriate references. We've worked with a number of universities to get formal proofs of the security and privacy properties of this formulation. So it could be called blinded public keys or something else. This technique is widely used in Bitcoin, which may or may not be seen as a plus by people. But we have formal proofs for a generalization that work with any elliptic curve and can again work with other algorithms. So we would like people to have a look at the draft and provide us with feedback. We're at the 0-1 stage now, and at some point, since this could potentially wind up being used by a number of countries in the European Union for their wallet instances and by FIDO as an extension. One of the interests we have is providing a raw signing function for FIDO, so that you could have a remote secure element. That's one of the problems that the European wallet projects will have, is that essentially there are 4 phones for sale in Europe that can actually run the proposed European wallets to the standards that are actually required for national IDs. And that's going to necessitate either network-based or external secure elements where you have to tap something to your phone to be able to do the actual presentment signing. So this is one of the potential ways of dealing with that. Are there any questions?
So just to clarify, you are not asking to adopt the document, but you're
No.
asking for reviews, right?
Yeah, I'm asking for reviews.
So maybe
think
Crypto
maybe-
Panel,
Hmm?
maybe Crypto Panel can help you out.
Yeah. So at some point, once we've got some more reviews and cleaned it up a bit, yes, we would like to ask for adoption, but this is probably a bit early for that. I mean, unless you love it so much you want to adopt it now. I mean, you could twist my arm.
I think chairs are awake enough not to adopt documents on the spot this time because we're so jet lagged, you know. Don't use it against us.
Oh, so I missed my opportunity. Okay, I get it. Any other questions? No? Okay.
Okay, is Mike Onsworth in the queue? Oh, he's here. Oh, Mike, you're up. So just to set this up, we had a call for adoption for a topic at the CFRG, which is not the typical way that this is done. Usually it's a fully fledged document that's being adopted and then modified and adapted. But there were so many different approaches and questions about how to do a hybrid classical and post-quantum safe chem that we brought it to a list. We had a pretty active discussion, and feedback on the list was plenty. And part of the reason why not having a full draft was useful is that it raised a bunch of requirements that may not have been known ahead of time. So some of the feedback we got included, a lot of folks said that we need general advice for why your combiner of PQ and classical public key cryptography for key agreement, not for signatures, why your construction's unsafe. So there were multiple different constructions, such as the one from Apple, the one from Signal, the one proposed in TLS, and it's not just a chem plus a chem. And not all of these had the exact same properties, so there was a need for general advice to protocol developers about how to do this safely. There's also a request for specific combiners to be specified so that implementers at the higher level could just plug things in safely and have a CFRG reviewed implementation, combining your favorite PQ, which in this case for a lot of folks is ML Chem, but there's other ones that are interesting to folks, and your favorite classical key agreement, whether that's elliptic curves or RSA, depending on what your deployment requirements are. And this is something that we do keep in mind at the CFRG, is to try to be as helpful as possible to IETF protocols and what their constraints are, and provide specific outputs for that. We also had a bunch of other notes, including some sort of tricky questions about ML Chem and IPR, which have not been dealt through. So Mike was happy enough to volunteer to come give a small talk about one aspect of this discussion. So I'll leave it with you, Mike.
All right.
I feel like I'm going to need sunburn cream after giving this talk. You set me up to be the whipping boy for this topic. I personally am not advocating for totally like hybrids so generic that you can just choose from a drop down at runtime. That sounds terrible. I'm sure the combiners do need to be tailored to the properties of the underlying chem.
Right, and
I don't want anyone to think that I'm still advocating for that. I was 4 years ago, but
right, and CFRG documents typically don't tell implementers which interface to use or how to implement cryptographic agility one way or the other. Yeah, from a generic perspective, there are ways to do this incorrectly, and we've seen a lot of them recently.
Yeah. Okay. So the topic that I'm here been asked to talk about is really quite specific. It's basically why X20519 isn't everything that we need. Why I think we should consider other classic things to hybrid with. I've just got really one slide here. Can I next? Basically, my point here is it's a migration stepping stone. So I work for Entrust. Most of you who know Entrust know us as a publicly trusted root CA, web PKI. We, of course, do other things. We've sold on-prem PKI since 1992. And there's lots of ecosystems out there that use on-prem PKI for all sorts of weird, custom, bespoke, weird, custom, weird, old things, like predating CMS, sort of old, custom, bespoke. They're still out there. They're still running. We've got to think about how to move them. I know it's easy to scoff and say, well, if you haven't done any modernization in 30 years, that's your problem. But it's also our problem as citizens of the world, because there's lots of money that traverse these things, right? I could also make an example of public SMIME, which to 3 significant figures is 100% RSA, as a thing that's, you can't just trivially say, well, your smart card should now just do elliptic curve. Like, okay, yeah, cool. So there are things out there, right, that are on RSA that may still be on PKCS1 encryption RSA, and we've got to think about how to move them. And yeah, they maybe shouldn't, but they are. So these, we've got some customers who have on-prem PKIs where like the QA lead time is 2 years. You want to implement new crypto, it's got to soak in QA for 2 years. That's after it's FIPS certified, which by the way, MLChem is not. We don't even have the FIPS spec yet. And then people have to write code and people have to get in the like 18-month or longer FIPS queue to get a testing lab. So I don't know when we're actually going to practically see, large deployments of interoperable FIPS and common criteria certified implementations of all this stuff. So figure the start gun goes in a couple months and then people get in queue and then maybe we'll have them in prod by 2026. And then it's 2 years of QA soaking time and then it's a year of pre-prod. It's entirely possible that even if we move fast, we can't get the stuff into prod until 2030 at the earliest. So the point here of hybriding the old stuff with MLChem is to try and shortcut some of that lead time. If you can take the crypto you already have certified, compiled, deployed, and just bolt that into MLChem, you can get MLChem faster by cutting off some of that lead time. I think I have one more slide. So that's really the sales pitch here, is that we're not saying that RSA PKCS1 is good. We're saying that it exists and we need stepping stones to help gracefully migrate it to the newer stuff. So we have this discussion about, should we make hybrids for RSA Chem versus RSA OEAP versus RSA PKCS1? What stuff, RSA PKCS1 I know is a tricky one because it's no longer FIPS certified or FIPS approved as of like 4 months ago. So it's weird for me spending up here advocating for it, but it losing FIPS approved status doesn't make it any less used everywhere. So these are sort of the questions that I have. These are the customer use cases that I'm trying to advocate for. If we can have this stepping stone, it actually helps us get off the old stuff faster in some weird counterintuitive way. And that's really all I'm up here to say. Can I go away before the firestorm starts?
The mic doesn't fit very well.
But that would be no fun. Rowan May, could you go back to the previous slide, please? So I understand totally understand the 2 years of QA and the 18 months to 2 years for the FIPS Q and all that. And then around the bottom bullet of this slide, there was a statement that deploying MLChem with RSA was faster than deploying MLChem with another, with another classical chem. And I don't see any evidence of that. I see evidence that it takes a long time to touch these devices. And I see no evidence that it makes any difference what other other algorithm you use, what other additional security improvements you add at the same time.
If I only have an RSA code today, my entire ecosystem is RSA, I don't have an elliptic curve code base. I now have to write one. I now have to get that FIPS certified. I then can do an MLChem with elliptic curve. Like you have the same FIPS certification lead time if I don't have elliptic curve today.
That's assuming that your code base even compiles today. That's assuming that your code base still compiles.
My code base compiles.
Well,
okay,
you're not talking about you. You're talking about the vendor.
I'm doing something very hand wavy, but
yeah, that's a real issue. Like a lot of the people that have this problem, their product cannot compile on any code base that will compile MLChem.
I think that's a different problem than the one I'm advocating for. I'm advocating for not having to touch the inside my FIPS boundary. I don't know if that maps to I can't compile my code at all, or if those are different problems.
I'll just conclude by saying I'm skeptical of the problem, and I think it might be useful for us to try to get more data about, who thinks, who at some more specific use cases.
I'll also say on behalf of my employer into the camera, we've been asked to provide, we're talking to our customers to see if any of them will come publicly with this. So these slides are super, not naming names. It could be useful if these customers are willing to put their use cases publicly, but at the moment I'm trying to be quite vague, right?
Rich?
Rich Salzakam, to address the last point, we might be able to be a blinding factor to help present some of the use cases. I think this is really cool. I think it's important. I think it's going to be sort of interesting for CFRG to talk about deployment in commerce. So I'm kind of curious where the chairs and you think this would go.
Yeah, this is a really big open question from the adoption call, and my hope is that we can work together with a design team that we put together. Still waiting for people to accept in the next couple weeks, and put together a reasonable set of requirements that is justified with practical reasoning behind it for what the outcome of this adoption call should be in terms of documents, whether it's one document that has advice on how to properly combine things as well as some examples, or two documents, one providing general advice and one providing specific specifications. So this is still not decided, and our hope is that as the design team comes up with a list of requirements, we can discuss it on the list and tear it down and come up with something that we can agree on moving forward, that the CFRG can provide something that's useful to not only the IETF, but the industry, and fill a particular gap, not replacing NIST or replacing other standards groups, but providing help where there's disagreement in terms of how to do this.
Okay, yeah, friendship would win aside. I wouldn't say NIST is helpful to the industry, but at any rate, yeah, I'd be in favor. I'd be happy to help work on some of this stuff.
Scott Fleur, Cisco Systems. I would support. We have the same problem that Mike is running into. That we would once MLChem is standardized, we'd like to ship it, but we can't be. It's not going to be FIPS certified. Mike says the queue is 18 months. I believe it's actually a lot rather longer than that. We need a workaround. And yes, our code does compile.
Stephen?
Hi, Stephen. I'm really confused by the talk about compilers. I don't care. Anyway, do we want to have every possible option defined? How do we? So I'm also confused about how we stop anywhere.
How do we stop
So-
anywhere? Yeah.
The question on my mind is, I think a slight rephrasing of that is, if we have good reason to believe people are going to do stupid things, should we try and help them do it less stupidly? Is that a fair rephrasing of your question?
It's a not unexpected reaction, but not a fair rephrasing of the question. No, the question is, it's entirely. I understand you have enterprise PKI customers going back a long time, doing all sorts of weird things. There's a lot of possible algorithms in the world. There's a lot of possible ways of combining things. I don't know where do we stop? Do we ever stop? Do we get?
Yeah, I think we stop, and I think we have to. And a lot of the feedback on the list was that more choices beyond a very crisp set is detrimental to, giving people too many options that they could do incorrectly. I think TLS 1.3 was an example of a protocol that tried to balance these two things, reduce the total number of selections and cut it down to, RSA, ECD, SAP 256. X25519, and then the 2 or 3 signatures, and that's it. And mapping those to what's expected to be deployed. And the long tail would be not something that the IETF would comment on, or the CFRG would provide suggestions. So, I think, where do we stop? I think our previous set of documents that had a number of recommendations, things like OPRF or hash to curve, had a relatively limited number of well-defined code points, and allowed other people to come up with different code points if they want, as long as they fit the general construction. I think this is something we could potentially do here. The risk of having only one construction is that this is not what everybody else is going to implement. So, in TLS, people needed P256, right? Or people needed RSA. It wasn't like we could go to require only X25519, although some browsers were able to do that. So it's a balancing act. This is from the chair's perspective. Okay, next in the list, we have online. Ron?
Hi. Yeah, I fully agree with this. I think we need to understand whether we want a different construction for each CAM combination, or whether we want a generic combiner that we can then instantiate and allow certain combinations. But the reason why I'm here in the queue is I think I would like to put the sense of urgency forward, because we have several protocols that are starting right now ready to go with their own CAM combiners. And if we don't if we don't do it now, we risk of them encrypting data ready to those CAM combiners and then having to persist them, basically not being able to change anymore.
Okay. Thanks for the comment. Jonathan?
Jonathan Hoylands, Cloudflare. Perhaps it would get more consensus to adopt these documents, or adopt whatever documents come out, alongside a die document that says these documents are valid for 5 years, and after that they are not CFRG approved, whatever that means. Just like literally say these have fixed lifetimes.
I think that makes more sense in the IETF than the IRTF.
The IRTF can do whatever they like, right?
but we are not the protocol police. We are not even the standards writing group at all. So, although CFRG does sort of straddle the line more so than other IETF groups.
Thank you.
Okay, if there's nobody else in the queue here, we'll continue this discussion online with the design team. And thanks so much, Mike. And we do have an extra presentation that was last minute, and we have the slides here, and we don't have the slides.
Everything list.
This is the last minute one, right? Yeah, Muhammad Usama Sardar, are you in the queue?
Yeah, I'm here. Can you hear me well?
Yep.
I sent the slides. I see that they are uploaded. Should I share from my side?
Yes, please. Yeah, we're having issues on our side.
Okay, sure. I think I need some approval.
Were you able to do it?
Yeah. Just a moment. I'm selecting. Okay. Do you see the slides now?
Yep.
Okay, perfect. Yeah, sorry for the last minute slides. So I saw there are some time, and we have done some analysis of combination of remote attestation with TLS, and we took it to the TLS working group. We didn't get any feedback, so I was just wondering if folks here from crypto background can give us some feedback. So a little bit of a background of why we are doing this and why this is relevant. The key idea basically is that I have there are few problems in TLS which we are trying to solve by using remote attestation. One of them is that TLS inherently does not validate the security state of the endpoints, whether it's server or the client, both sides, their software and their platform. And for many use cases, such as confidential computing, we need a more comprehensive set of security metrics. And second issue is that TLS is inherently very complex. There have been like 15 different exploits so far already. And the question in our mind was that is all the complexity, for example, the key schedule, justified? And for the first point, for example, like there are three ways of combination of attestation, which gives a more comprehensive set of security metrics with the TLS. And this diagram is showing time going to the right. And in between, there is this TLS handshake protocol and the two parts like key exchange and authentication here. And one can do the signing of the evidence, which is for remote attestation, signing all the claims. It can be done before the TLS even starts, which is this labeled as pre-handshake attestation. And one can do it during the authentication phase when the certificate message is being sent. At that point in time, that's called as the intra-handshake attestation. There is an IETF draft in the TLS working group, not yet adopted. It's still an internal draft, which describes how this is going to be done. And we started the formal analysis for that specific protocol, which was also an ongoing work. and where we hit this TLS kind of thing where which I will just describe. And the final option is to do it at the very end when the TLS handshake has been completed. One can then sign the claims and generate an evidence at that stage, which is the post handshake. All of the solutions in the confidential computing domain are valid, like Intel's RATLS, for example, is pre-handshake attestation. The IETF draft is in the intra one, and the confidential containers project from CNCF is one example of post-handshake and is also widely used. So our focus for this presentation, for example, is on the formal analysis, and there are a lot of things here. What I just want to focus is we started with the validation part of formal model, which was developed by India like 6 years ago, and then we saw that the core idea was to see whether it matches the specifications and whether the model is good enough. So this part, the formal model that we took from India, we basically wanted to integrate the remote attestation part into it and then validate it and use it for our properties. And the tool we use is Proverif. So all other blocks are currently irrelevant. I just want to focus on this validation part, which is relevant for this. And very simple validation framework. What we did is we took India's artifacts, each and every key which is generated by that, we just simply compare it with the TLS 1.3 specs taken from the RFC, and we compare each and every key coming from both of the sources. And if there is a match, we have a constant success to represent that. And if there is a mismatch, we have a constant failure to represent that. And we keep repeating this procedure for each and every key, starting from the first key going up to the end of the key schedule. So with this, what we saw that there were a number of failures within the key schedule right from the very beginning. And then we tried to explore what the reason is, why this is the case. And you might be wondering where the right side, for example, this TLS 1.3 specs come from, how the keys are generated there. So from the RFC, what we did is the RFC in that figure, I think in section 7.1 describes the first stage. We added the second stage from other sections and so on. And then we compared each and every key which is coming from the India artifacts to this. And we found that the issues were basically related to the handshake secret and the master secret. And because of that, actually, since like the handshake secret is here, the master secret is here. So once these keys are wrong, so any other key generated afterward is also wrong. And the key point that I would like to discuss or get feedback on is basically what they have done in their artifacts is the derived secret stage for both of the derived secret stages, which is actually here, the salt for the HKDF extract for the generation of handshake secret, as well as the derived secret for the generation of, which generates a salt for the HKDF extract, also for the master secret. Both of these cases, instead of taking a 0 here, which is according to the specifications, they have taken an extra hash over that. And this is something we have not yet been able to figure out why this extra hash would be required for any purpose. Like we have explored all the options and exhausted all our thoughts that we could, for instance, even from abstraction purposes, and we check the time of verification for both cases. If this would in any case help them do some abstraction, I mean, do verify it quickly or somehow something like that, we found that the time gain in both cases is nearly negligible. And in the second case, the second issue is that, which is kind of, we have no idea here again, the master secret generation is being done in such a way that it skips this derived secret. I completely understand that at symbolic level, they are one-way functions. It makes sense to, combine these two blocks, represent as one, or even ignore this kind of derived secret completely. But my question is why this specific derived secret is being ignored and not this one. So these are the kind of questions that I am still struggling with, and we haven't been able to find any good reasoning for this, why this would be the case to skip this and not this in the same artifacts. And this is something that we took over to the TLS working group, as I said, and we mentioned all the, not all, some of the issues, both of the issues that I have described above. And I was wondering if someone has any thoughts or experience regarding this to share with us some insights.
There's one person in the queue, Jonathan Hoyland.
Jonathan Hoyland, Cloudflare.
Yeah.
So I'm not one of the authors of this paper, but I did study it quite closely. And I was under the impression that they were implementing draft 18, not draft 20, which you put in your email. So that might explain some of the differences.
Yeah, that's right. So just to clarify, so the paper published in SNP was draft 18, but they later extended their artifacts to draft 20. And since we would naturally take up the draft 20, which is closer to the RFC. So that's why we have taken up this draft 20 artifacts rather than draft 18.
Did you check whether the draft 18 artifacts do capture draft 18? Because I think they do. I think the draft 18 artifacts are pretty good.
Actually, the change for this derived secret was actually done between draft 18 and 20, which is more precisely in draft 19. But this is still a question for us, like, why would you implement draft 20 in a way which takes this derived secret and not this one?
Right.
So
and then
I went through all the discussions which were done for draft 19 in the mailing list. But that kind of still doesn't make much sense to have this one and not this one, even if they have any kind of
I assume it was just a piece of work they didn't quite finish. But the other thing with the strong hash, I believe they have in their paper a whole section on modeling what if you use TLS 1.3 with weak with weak primitives, and so it's probably just a way for them to capture whether you can use weak primitives and it will still be correct. So I wouldn't read too much into it.
Yeah. I mean, that's completely fine. I went through that thing as well. So that's completely fine. But the question is, I mean, you can model weak Diffie-Hellman and weak groups. That's weak hashes. That's fine. But the question here is that according to the specs, it would not be a hash here. So my question is not about strong, why this is strong hash or weak hash. The question is that it should have been, according to the specs, it shouldn't be any hash at all. We also looked at their implementation of the derived secret function. We thought that maybe, so derived secret by definition itself has the hash over this. So we also looked into that. Maybe they took a hash over here because they changed the definition of derived secret so that the hash is taken inside the derived secret. So it's not looks like this from the outside, but inside it's equivalent to the specifications. But it was not the case. I mean, they have a double hash, which is one is inside according to the specs, and additional one hash is here, which doesn't make sense to us.
As I say, I'm not one of the authors of this model, but if you want a model that's much better, you should go look at the Tamarind model. Not that I'm biased, of course. But yeah, I wouldn't read too much into the draft 20 stuff. I think they never published a paper on it as far as I know. So I think just assume it's not finished yet.
All right. Any other questions? Thanks to Mohammed. All right, we have 4 extra minutes. Any other business? Going once, going twice. All right, thank you so much for this great session of CFRG, and we'll see you again online.